Hello, everybody. Mr. Hinnon here for the latest notes on capacitors and dielectrics. So specifically, the other part of chapter 19 that we're going to get at is capacitors. Capacitors are an electrical device that is used to store charge. We did a little activity with it, or if you were the remote group, you looked at this simulation to kind of look at what factors affect it. Now we're going to go into looking at those factors. And then also I'll talk about this thing called a dielectric. We didn't really get into that very much yet. So the simplest capacitor is what's called a parallel plate capacitor. It's basically just two metal plates. So you got a plate here and a plate over there. One has a positive charge. Move myself out of the way. One has a positive charge, one has a negative charge, because you're connecting them to some external voltage and you're using that to charge it up. Now the space between them can be filled with air, or it can be filled with some kind of material that's an insulating material. So it has to be an electrical insulator. This is known as a dielectric material. Couple of things that are going to be important are the size of the plates is going to be important, and the plate separation. We saw that a little bit with our activity. Those that were in person, we did an activity where we actually made a very simple parallel plate capacitor with aluminum foil and paper. And the plate separation is important and the area was important. I wanted to do that without you knowing why those are factors. For the remote group, you played around with the FET simulation, you should have hopefully seen that same thing, and you can actually see what kind of factors affect it. Now, the true relationship for a capacitor is this little relationship here, that the charge that you can actually place on either plate, the quantity of charge, is proportional to the voltage or potential difference across the plates. And this relationship between Q and V, the charge on each plate, so it's not the total charge, but actually the quantity of charge on either plate over the voltage, is a thing called the capacitance. It's how much it actually stores. So here's our equation right there. Sorry about that. This thing doesn't like to remember that I still have the pen. So this is our equation. But really where it kind of comes from is C, the capacitance, is the quantity of charge on each plate divided by the voltage or potential across the plates. So that's a good way to think of it. So capacitance is measured in a unit called the farad, which we did a little, you saw a little bit in the FET simulation and in class, and it's named for Michael Faraday. Michael Faraday is a famous physicist who did a lot of work with charge and magnetism and that type of stuff. And basically what it is, they took part of his name and call it a farad. So it's labeled with a capital F. This is one way to do it. But unfortunately, unless you have a voltmeter so you can measure the voltage and some kind of device for measuring charge, that's not an easy way to do capacitance. So there's another way to look at it we're going to get at. And where it comes from is this idea. This little equation right here is actually coming from one other idea. If I have a positive charge here on this plate and a negative charge on there, I'm going to create an electric field. I'm going to have electric field lines that are going to go from positive to negative, as you can kind of see in that picture. If I take some shape and put it in here, what I then have is I have an electric field passing through some surface, some area. That's called electric flux. So there's going to be some kind of electric flux going through here. And if you remember, the definition of electric flux is it was the product of the electric field and the area, and then the cosine of the angle between them. Now, in this particular case, what we're going to do is we're going to align the area so it is perpendicular, or it's basically perpendicular to the direction of the electric field. And since the direction of the area vector is perpendicular to it, they're going to be parallel. We won't have to worry about this little cosine. So I'm going to get rid of the little cosine part. The other thing, if you remember, electric flux was equal to the total charge enclosed divided by the permittivity of free space. Well, if I divide this over, in other words, if I think of my area as kind of covering everything, I can bring this over, and what I end up with is the electric field being produced by a parallel plate capacitor is Q over this epsilon zero, that's the permittivity of free space, times the area of either plate. And so this is an easy way of kind of finding the electric field. You go, okay, why do you care about the electric field? Well, the electric field is what's going to affect how much energy you can actually store, or how much charge you can actually store, or how much capacity the capacitor has. The other thing that's going to be a factor is the dielectric constant that's in between. So if I have something in A here, I have an empty one. This is empty, there's nothing in between, and basically you have a positive plate creating an electric field, so this is our electric field. When you put some kind of dielectric in here, since this is an insulator, what's going to happen is one side of it is going to gain negative. Basically, they're going to align so that the negative is near the positive and the positives are near the negative. Well, now if I look at that, I'm going to switch out the color here. Inside of the dielectric, it's actually going to create a little electric field that's going to be pointed in the opposite direction. So these little blue lines are the electric field inside the dielectric. Well, that combined with this electric field is going to make it weaker. So inside of here, you actually have some of it kind of canceling. So basically you have this going this way, so that cancels out some of that. So it makes it weaker. When you have a weaker electric field, it tricks the capacitor into thinking, oh, you can store more charge, and then you're able to put that on there. And we get a thing called the dielectric constant, and the dielectric constant is really a ratio of the electric field with nothing in there divided by the electric field with it. Since the electric field with it is always going to be smaller than when it's empty, this number is always going to be greater than 1. So putting a dielectric constant in there is going to change the electric field. Now let's take those two equations and put them together. Oh, and here's just an example of some dielectrics. A vacuum, which is having nothing, would be 1. Air is basically 1. And then different materials are going to change it. Looking at this one's kind of amazing. You have some liquids here. You can actually make liquid capacitors with alcohol or water that actually have really high dielectrics. Most of the time we don't do that. We tend to use paper. This was the one we created in class, or some other kind of material, maybe Teflon, or we use wax paper, all these different insulators are good ways of doing that. So now, if kappa, which is the K, that's the dielectric constant, is E0 over E, then you can rearrange it and solve for E. The electric field would be E0 over the dielectric constant. We put this in for E0 because that's the electric field when you have nothing in there. And electric field when you have a setup like this, we saw this when we were doing the Millikan experiment. The electric field is also equal to the voltage difference. So this is the voltage across these plates and the distance between the plates. So the D. So that ratio is also another way of measuring the electric field, or volts per meter is another measurement of electric field. So if we do a little bit of substituting in here, we can actually find a relationship between charge on one side and voltage on the other. Since we know Q over V is going to equal your capacitance, we get another way of finding the capacitance. This is going to be a very important equation as we're doing this. Notice that the capacitance, which is related to how much charge it stores per unit volt, is going to increase if you have larger area. So you make your capacitor bigger, you're going to be able to store more. If you have a very high dielectric constant, so the kappa, that is going to affect it, or if you put them really close together. So if D is really small, all those are going to affect it. We saw a little bit of this when we were playing around with it in class. Some people even kind of played around with that a little bit using the wax paper versus other stuff. So I actually have already gone through this. I don't see why I have it in. This is just a little sample problem. One use of capacitors is the keyboard. Is sometimes some old keyboards, when you push down on them, you were actually shrinking the distance between the parallel plates on a capacitor, and how much whenever you did that, it would signal, hey, this is actually being pressed, and you had to push it enough to actually get that to happen. This is just an example. If we have it shrink between two different sizes here. So this is the size it has when it's pushed down. This is the size it has when it's not pushed down. We can see there's a difference in the capacitance. And when we get pushed down, we get a greater capacitance. 10 to the negative 12 would actually be a picofarad. So these are picofarads here. So basically what it did is it went from about 20 down to about 6. So we had a drop there, and we could figure out the change, about 19 picofarads, and so we could calculate it. So this is going to be an important equation that we're going to be playing around with when we get into capacitors. The other part that we'll have, and we'll spend some more time on this when we get into the problems dealing with capacitors, is you store energy. You store electrical energy in this capacitor. And there are 3 different major ways to find that electrical energy. Where it's coming from is we know that the electric potential energy is going to be related to things like your charge, your electric field, and the distance between the plates. This is actually going to be related to your voltage. So this is going to be Q times V. And so now we can kind of play around with different things when we're trying to find this energy. The reason why you have these 1/2s in here is, think about it, when you have an uncharged capacitor, it doesn't have any energy stored in there because you have no charge, and it's going to build up from 0 up to some maximum value. So the maximum value is related to the charge and voltage, but as you build up to that, you're going to go from 0 up to that maximum. So we talk about the energy being half of that, or the average of that, if you want to think. That's a little bit on capacitors. We'll work some more on this. It's not going to be a part of our Chapter 19 test. It'll be kind of its own little separate part. And then we're also going to go into circuits soon, and we're going to look at resistor circuits as well as capacitor and resistor circuits. Hope you enjoyed.